really good shape. Oh my God.
So, we were talking about one axis of flight earlier, correct? You guys remember which one that one was? The axis of flight? Longitudinal, okay? Remember, that was a straight line that was through the nose and all the way back from the tail. And it's a straight line that goes off in every direction. And that describes the banking motion of the airplane, right? Or motion that's caused by the ailerons with some rudder input. Oh, gosh. There's always like a little extra something. It's like, man, why can't I get everything at once? Okay. But anyways, yeah, this is ailerons primarily, changing me back and forth. All right. And there are a couple other axes, right? What other axis do I add? Somebody said something that made me excited. Yeah, I got a vertical axis. Which way does vertical go? That's pretty easy. Straight up and down? Vertical? Okay, so the vertical axis is just like this. And I've got a control surface, and we talked control surfaces yesterday. So we said these are ailerons that are making me move left and right about the longitudinal axis. And then the vertical axis, I have another control surface. Which one's that? The rudder, okay? So that rudder is going to cause the motion around my vertical axis, okay? There's one more axis. Anybody? Lateral, okay? So lateral, everyone okay with the word lateral? Kind of decent? Okay, not too bad. Lateral is this, all the way across left to right, okay?
They cross from the center of gravity. Yeah.
They do. That's fantastic. So lateral axis, this describes my pitching moment, or the pitching motion of the airplane, pitching up, pitching down. And I have a control surface for that.
Elevator.
That makes me go up and down, the elevator, right? All right. Now, which one? The stabilizer is going to help me for stability. On the back side of that stabilizer is an elevator. And then those two things could be formed together for a stabilator. All right, like I mentioned yesterday, we're not going to talk too much about stabilator because you just won't use one in the private pilot. Right? Not unless you're flying a Piper airplane, and most people are using Cessnas. So the elevator making me go up and down. Now, something that's interesting is that all three of these axes are going to join at one point. And that center point is called the center of gravity. So all motion around this airplane goes through the center of gravity. Kind of planting a seed there in everyone's head. If I'm going to load my airplane with the center of gravity towards the back, now all the motion will occur by that center of gravity, okay? So every bit of the motion will happen around that center of gravity. If it's towards the front, all motion goes through that center of gravity. That's where the three axes intersect. Okay, so a little teaser right off the bat. Here we go with stability. Key terms, of course. Stability. Static and dynamic, positive, neutral, and negative. I am going to touch on that, and then we're going to get right back off that subject, okay? Because we need to know and appreciate a little concept of it, but oh boy, we can get into it, all right? So maneuverability, controllability, longitudinal, lateral, vertical axis, okay? Center of gravity, that's where all three of those axes meet. Longitudinal stability, I love to demonstrate this in an airplane. We'll talk about it in the classroom. Demonstrating in the airplane is great, all right? Center of pressure, that's also what they're going to call center of lift, okay? Just the same concept. Where's the very center part of the lift, okay? CG range, so center of gravity, there's an acceptable range. I can load the airplane to here and here. Anywhere out of that is not acceptable, okay? Tail down force, which helps describe my stability. This is how engineers built these airplanes in such a manner that they will be predictable and exhibit positive static and dynamic stability. Thrust line, how do if I add thrust or if I take away thrust, how does that cause a pitching moment in the airplane? Lateral stability with dihedral. Sweep back. When you start flying one, we'll get a lot more into it. Right now, we'll probably just take a picture of it and then see how it works with a yawing motion. Directional stability, Dutch roll. Dutch roll is fun. And how do I avoid a Dutch roll? Well, I fly the airplane coordinated for sure. Spiral instability, power off, power on stalls, part of your program. Accelerated stalls, cross control, secondary stall, spin. These are all demonstrated stalls. So the instructor will demonstrate those stalls to you. I think it is stage 1, lesson 6. I always try to do that one because it's a whole bunch of fun. You will get that before you're in solo. You'll be introduced to all of the demonstrated stalls. You don't need to do those, but you'll see what they look like, okay? A spin, erect, inverted, flat spin, or incipient spin. We'll go through the spin phases. Fully developed in spin recovery, okay? So we're going to start talking a little bit more about spins, and we're going to talk a whole lot more about stability here. Okay, this is a desired flight path for the airplane. What's happening with my pilot here? What are they doing? Well, they're all over the place. Okay, that's natural. That's going to happen. Usually, this happens as a result of a pilot doing too much with this. Just stop. Let the airplane fly, and it will probably do better than you. And no, not even with an autopilot. Okay? But I've got an updraft. Now, we're going to talk weather at one point in time, but let's think about this for a minute. If I went outside on a hot, sunny day, and I stood on the grass without wearing any shoes, that would be okay, right? I can stand in the grass, no big deal. But now if I walked across the black pavement, how hot is that black pavement? Very, very hot. Hot air rises. So it's natural for me to have an updraft, especially on a hot, sunny day. These are just turbulent conditions that I'll experience all the time that I'm flying, especially in the hot Florida sun. Okay, so I get a little updraft by this road. Okay, some convection that causes the airplane to move upward. If I don't touch the flight controls at all, okay, which is okay. I got control of the airplane. I'm not letting them go completely. But if I don't apply any pressure at all here, the airplane will naturally return towards the desired flight path. Okay? And then believe it or not, after a period of time, and you can kind of see this is much more than that one. This one's a little bit less, and that one's even less. After a period of time, the airplane will return to your desired flight path because of the way that the engineers have built this thing. Okay? All right. Longitudinal axis. This describes a banking motion. What flight controls am I using here? Okay, good. And if I have the controls turned to the left, which aileron goes up? Left. Thumbs up, ailerons up. Okay? All right, lateral axis. I got the lateral axis. This controls pitch with an elevator or stabilator. We're going to call this one an elevator. That's fine. Vertical axis. This causes a yaw, Y-A-W. Or I can call it directional stability. This helps me maintain my direction. Now the airplane it has a propeller on the front, so it's going to move that direction, whichever way the propeller is pointing. But if I have a little bit of left or a little bit of right, it's imbalanced. It's not balanced properly. It doesn't really feel comfortable for the passengers either. Okay? Some of these things will happen as a natural phenomena of using your ailerons. That's called adverse yaw. Okay? And it's one of my favorite things to make sure that pilots know before they solo. All right. Here we go. Let's talk real quick about this guy. There's your longitudinal axis. Here's what's happening with the right wing. I've got an aileron. Here's what's happening with the left wing. I've got an aileron. We were talking, if I'm going to bank this airplane to the left aileron goes up. The right aileron goes down. All right, so similar stuff that we discussed yesterday. Left aileron goes up. What does that do with my chord line? And what does that do with my angle of attack? A decreased angle of attack. Okay? So let's think if that makes sense. It should. I'm going to take my ailerons and move them to the left. I get less lift over there. Is that what I want? Of course. That makes sense. Okay. Here's where it gets interesting. The right wing is going to make more lift because the aileron goes down, which adjusts the chord line. That increases the angle of attack, causes more lift. And what do I get every single time that I create more lift? More drag. Which way are we turning? That's correct. That's why I put my left and right on here. So I don't, let's see. Right? So I got left. I'm turning the airplane left. Which wing gets more drag? You see what the problem is? A lot. A lot more than you know. And I know that because I get in there, and where do I got my student? I got my student, and they got both feet on the ground. Oh my gosh, what is going on here? All right, let's bank left. All right, great. And the airplane is all over the place. Are we flying? Oh, yeah, this is great. No, this is terrible. You're making me sick, okay? So if I push left aileron, what should I do? It won't do it by itself. Okay? It won't do it by itself, I can guarantee you. So you have to push a little bit of left aileron as well. The same thing if I do it to the right. If I go to the right, I got to have that right aileron, right rudder. When I release one, what am I doing? Releasing the other. So when they say coordinated controls, we understand what coordinated means. Okay. That just means using two things together at the same time. But I have to do that. We don't have a yaw damper on this airplane. There are no fancy electronics or anything else, no gizmos. There's not a wizard in the back that's moving this thing for me. So instead, left aileron, left rudder, they go together, and I release them both together. The same thing if you turn to the right. All right? There are more forces than just that one. There's a couple because we have a propeller on this thing that make it interesting. But the adverse yaw is a very, very important concept, and so many times is confused because, shoot, I just got in this machine. You know, I wanted to turn left, and this looked like a good way to do it. I get you, but every time you turn it to the left, it's yawing to the right. And then when you straighten up your controls, it's coming back down. Now you're telling me you can't control the altitude. Well, there's a reason why you can't control the altitude. You're not using coordinated controls. All right? So important that we're using the coordinated controls there. All right. There's your lateral axis. Again, lateral, left to right, right to left, whichever way. That's the lateral axis. That comes in contact with the longitudinal axis, and both of those come in contact with the vertical axis. Remember, these things all come together at one point. So this is elevator. That's fine. Forget trim tab for the moment. Forget trim tab at all, but I have an elevator there, and if I increase the angle of attack, well, that's going to cause a pitching moment. But I've got a down force. And excuse me just for a moment. I'm going to plug this in before we lose my battery. I must not have plugged in this morning. But anyways, we got a down force on that tail. Okay? So, if I can find this thing. So the forces that are acting on the elevator point downwards. The lift on the airplane points upward, right? The wing The lift goes up because that's opposite gravity. But the lift on the tail force points down. Remember, this section is stability. So the entire section is discussing stability. But we don't have any kind of stability at all if I don't have an offset from center of gravity and these lifting forces. Okay? So let's go through this kind of like we did with the ailerons and examine the elevator. Here's the elevator pitching down. I'm trying to pitch the nose of the airplane down. What do I do here? I have increased lift, but remember the total lift on that force, on this tail section, is downwards. So if I increase a downwards force, what am I getting? Essentially less down force. Are you guys following? I hope so. I know the charging thing or whatever, but here, for us to understand any of the stability, it's very, very important that you don't get this confused with the tail force making lift going upwards. Okay? Because it does not. The tail force is causing lift in a downward motion. If it didn't, this airplane would not behave in a manner that's predictable. It would not exhibit positive static and positive dynamic stability at all. It would be borderline uncontrollable, and it would consume all of my resources and mental capacity trying to keep it in the air. Okay? So this lift that we're showing here is actually just less of the actual tail down force. All right? Remember, one of our key terms was down force, that tail forcing down. Okay, vertical axis, yawing to the left. Rudder is a rudder. So if I want to increase lift in one direction, that's fine. The tail will move in that direction and the nose will move in an opposite direction because it's on opposite sides of that axis. So if the tail moves this way, the nose is moving the opposite direction. All right? And there I got my rudder and increased lift, increased angle of attack, chord line, and so forth. That vertical axis comes in contact with the longitudinal and the lateral axis. Again, tremendously important for our discussion of stability. Okay, let's bring this thing together for a little bit. Center of pressure, that's the center of lift. I don't know why they gave it two different names. They just did, probably to confuse somebody. Center of gravity, look where it is in relationship to the center of lift. It is towards the front. Okay, there is a range. There is 100% an acceptable range. And we can see on the next slide, you've got a center of gravity range where I can load the airplane forward or aft. Because I might have bags in the back. I might have people in the back. I might have more or less fuel. So there is a range, an acceptable range where I can load this thing. But that range will always have that center of gravity in front of the center of lift. Let's talk hinge points for a moment. What do I mean by hinge point? If I tell you that I am describing the lateral axis as a hinge point, does that make sense to everyone? No? That's okay. Sometimes it will, sometimes it won't. What's a hinge? Do we have any of these inside the room? It's a door hinge, right? Where the door opens and closes. So just for a minute, imagine that that center of gravity is the hinge where this door is hanging off of, right? So if I open the door, I can't move this door off the hinge. I can apply a force to the door, but it's not going to move the hinge. It'll move the door around the hinge. The same thing if I close the door and I apply a force here, it's not going to cause that door to come off the hinge. The hinge stays right there. The axis stays right there. We were talking axis in that last section. We said the axis remains steady. It doesn't move. But everything around it moves around it. That's what happens with this airplane. If I'm okay with hinge, and we're going to start talking about arms and moments and so forth, but if I'm okay with this hinge, now I know no matter where I apply forces, all of those forces are going to cause this airplane to move around that hinge. Okay? So if I apply force here with this wing, and I push up on the wing, what happens to the nose of the airplane? 100,000% of the time, yes, guaranteed. Okay? Is that 100% clear? Okay. So, what do I have back here that'll resist that nose pitching downward? The downforce. Okay? So the horizontal stabilizer is always in a state of producing lift down. All right, so you're getting less down lift, okay? And I can tell you exactly how this thing would never produce uplift. Because if it produced any kind of uplift at all, it would be a tragedy. It would absolutely spell disaster for any pilot that tried to fly this thing, okay? Okay. And we'll talk about it with stability. Keep that in mind because we're going to revisit. All right, here we go. Center of gravity. You got a forward limit, you have an aft limit. Some airplanes can be loaded into different aircraft categories. Remember yesterday we talked about categories? Category and class with aircraft certification. So this is an airplane. That's fine, but it's a utility category airplane here. And if I load it to this top region, a little more weight and different forward and aft CG limits, I can load it to normal category. So different categories based on where we load. Now, what does this normal utility category mean to me anyways? Well, normal category means I'm limited to a positive 3.8 G loading and a minus 1.52 G loading. So I can only exhibit so much positive or negative load on the wings based on my bank angle and other control inputs. In the utility category, I can go to positive 4.4 to minus 1.76. It all deals with airplane structure and rigidity. Can this airplane effectively be exposed to 4 or 4.4 times its normal weight? And if it can, well, then you can fly it in the utility category. Okay? Flying in the utility category, I can do intentional spins. Okay? In the normal category, I'm prohibited to fly in intentional spins. There is an opportunity for a pilot, if they're flying in the normal category, to exceed the structural capability of that airplane. Bend it or break it, okay? You can do the same thing in the utility category, you just get different loading values. All right.
Sorry, can I have a question?
Yes.
This chart is for one exact plane or it's for...
No, this is for one exact plane. That airplane is made up. Who knows what that thing is? That's something. Every airplane will have a different weight and balance. Yeah. No, every airplane model. That's it. So all 172s will have the same category and the same forward and rear limits, but yeah, each different make and model will have its own. All right. If you're outside your CG limit, you break the nose gear. Okay. You just don't have enough force back here with this elevator to increase that pitch angle. You just don't, okay? If you have an extreme aft CG, the airplane may be very difficult or even impossible to recover from a stall or a spin. So here I'm trying my best to get this airplane nose down, but we just cannot do it. There's not enough lift. There is an aerodynamic limit to these control surfaces. I only have a finite amount of lift that's available here. Okay? All right. Here we go again. Tail down force, chord line, negative angle of attack, longitudinal axis, center of gravity, center of pressure. Again, it reinforces the idea that I got that tail down force. Let's go through a scenario for a moment, if you would. And that scenario is, let's change the equilibrium. I'm flying in cruise speed, level flight, and I change the equilibrium. Okay, everything was equal, now I change it. And I'm going to do that in my example, and we'll do the same thing in the airplane to demonstrate stability. I'll do that in my example by decreasing my power setting, okay? Which I think is a terrible way to begin a descent, because I usually want to keep the power as fast as possible. I'm trying to get somewhere here, man. But in this example, just for training purposes, I'm going to decrease my power setting. Because I'm in a carbureted model airplane, I'm going to put on the carburetor heat first, apply that, and then decrease my power setting. Okay, so I've reduced the power in the airplane. I've reduced the thrust. What do I get automatically as soon as I decrease the thrust on the airplane? Well, I get a decrease in relative wind here, and I get a decrease in relative wind there. Remember, that propeller is a 6-foot piece of steel. That is producing a tremendous amount of thrust, okay? I get it. It's not a jet engine, but it's producing a substantial amount. So the relative wind is affected as soon as I decrease the power. The airplane right now is flying the same speed because I just reduced the power. But this fan is blowing less over my control surfaces. Okay, we all agree? That's called the accelerated slipstream. All right, if I produce less relative wind, what's happening with my lift? A lot. So let's say I had 120 knots airspeed. So I got 120 knots worth of wind blowing over this thing. And then I reduce it, all of a sudden I only have 60. Well, I have half as much speed. How much less lift do I have now? 1/2 squared is 1/4. That's a big change. I got a whole lot less lift now. All right? So lift is decreased. That's fine. Lift here is also decreased. So the airplane begins to move downwards, and it begins to accelerate downwards because of gravity. And I also get less tail force. Here's my less tail force idea. If I have less tail force, what does that cause?
Pitch down.
Okay? I still have tail force, but there's less. So effectively, I have a lifting force back there. Right? The tail of the airplane will move up. The idea is, what did I try to do with this airplane by reducing power? I haven't touched any controls yet. I have not. I have my hands on the controls, but I'm not pushing any pressure. So what have I done with this airplane? I've initiated a descent. Okay? Decrease my power, right? And the nose of the airplane decreases by itself. Okay, magic, right? No, it's stability. Engineers designed it to be that way. What happens when that's called positive static stability, by the way. I wanted a descent, I commanded a descent, and the airplane cooperated. It went in the direction that I desired. Okay, that's fine. What happens when airplanes point downwards? It'll increase speed. So now I got an airplane that was pointing downwards, it's increasing speed. I get more speed, I get more. So that means I get more tail force. What happens with the nose? Goes back up. Okay? So this begins the process of positive dynamic stability, which means after a period of time, the airplane will fly in a straight path down. Initially, it goes down, but it won't go down too far. It's designed to go down too far. Then the aircraft will increase speed and it will pitch up, but not all the way level. It'll be less than it did last time. Then it goes down a little bit less than it did before. And after a series of oscillations, it will have a perfectly straight path. Okay? The airplane is stable. That's positive static and positive dynamic stability. Okay? Well, this is really interesting because I've taught a lot of different groups of people. Private pilot, instrument, commercial, right? ATP, certified flight instructors, all. One of the most interesting ones that I flew with was a Navy pilot. It wouldn't be a Navy guy, yeah. So a Navy pilot, and he wasn't a fighter pilot, but he flew something out there, I don't know, surveillance or transport, whatever he was flying. He had a video, it was unclassified, but he had it on his laptop of two F-14 pilots, or two F-14 crews, right, that were practicing maneuvers, and it didn't end well for one of the crews. They were at somewhere in flight levels, who knows? They were at high altitude, a lot less air density, because there is an air density function of this. So a lot less air density, and they were just spinning the airplane, doing regular spins. And an F-14, everybody's familiar with the Grumman F-14? Right? Okay, so you got an F-14, they're out there, they're doing their spins. The pilots were not able to recover from the spin. And you can see in the video, it was just spinning and spinning and spinning and spinning. And what in the heck is going on? It was almost uncomfortable. I was like, that airplane shouldn't be spinning for all this time. Okay, after some real video, right? After some period of time, the canopy comes off. And then two pilots come out of it. And then guess what happens? The airplane started to fly. Well, air density could have played something into it, right? But these two pilots were doing everything, trained professionals, right? They read the Aviator book of aerodynamics for naval aviator. I guarantee it, you know? And they were trying their best to recover this thing. And eventually they ejected, and as soon as they stopped messing with the controls, the thing started flying again, okay? I promise you that if you decrease the amount of control pressures that you're putting on the airplane, and instead just measure and try to be precise and exact with how much you put in, and deliberate, then you'll enjoy the experience. If you're trying to always control the airplane, you're just fighting yourself, okay? Anyways, true story. Here we go. You got your wing downwash, like we said, that comes over the stabilizer, and you got the accelerated slipstream. Like I was mentioning before, the accelerated slipstream causes an increase or a decrease in airspeed as we fly the airplane. That is, if you're not convinced that propellers produce a significant amount of thrust, then just stand behind a small Cessna when it cranks up, and you'll be like, wow, that is a good amount of wash that comes off that thing. All right, here we go. It shows me nose up pitching tendency with increased power. Nose down pitching tendency with increased power. This has a little bit to do with my downwash, but a lot more to do with where that thrust line is relative to CG. All right, so we said that center of gravity is more like an axis, or like a hinge. If I apply some force, I can't move the hinge. The airplane is going to move around the hinge, just like that door does. Think about that CG exactly the same as the hinge on that door. I push on the airplane here, it's going to cause a decreased pitching attitude. Now look how much arm we have. And by arm, I mean, how much leverage do I have on this thing? Not a whole lot. So this is relatively insignificant. You're not going to appreciate this very much. It's very, very small, almost an academic exercise. But it is a true thing. The 737 MAX, what's the problem with that thing? Well, besides they took an airplane that was supposed to be a regional airliner and they just kept making it more efficient. What does more efficient mean? Bigger engines on it. Okay, that's what they've done. They kept putting bigger engines on. In fact, the bottom of the engines were flat, right? Remember, the bottom of these things were flat because the engine was so big they couldn't make it round. And then the last engine that they put on this thing was so big, they couldn't fit it under, the landing gear folds up on a 737 like this. So the landing gear touches in the middle. They couldn't put bigger landing gear on it and make it stand up taller. They had to put bigger engines on it, more efficient. So the engines they put on it, they made the engine go more forward. And then when pilots applied power with this thing, it created a tremendous amount of pitching up moment, right? So this is a true story. Again, one of those things where kind of nice to know, but we're not going to experience this as much as you experience the prop downwash. You'll experience that a whole lot in our Cessnas. Okay? All right, let's talk. Side slips. Whew. What in the world is a side slip? That means that the airplane is moving somewhere other than a straight line. So the airplane is moving somewhere like this, and again, not relative to the ground, because I'll have a wind correction angle. Okay, that's fine. But relative to the wind, relative to that relative wind. So in relationship to that relative wind, I have a side slip condition left or right. The way that airplane wings are formed and the way the airplane wings are created, I'll have some relatively good controllability features that will allow me to fly this airplane well. Relative wind here, as the aircraft enters a side slip, it will allow that one wing in a low bank condition to create more lift because of the dihedral, which is just the angle that's formed straight from the horizon to that wing. You guys see the dihedral, okay? So I get increased lift on this side. It's still lift. I mean, it's a wing over here, but it'll help straighten up the airplane and roll it level. This is another function of engineers building these things so that it will fly straight without you. Okay? All right. This says that the 172 is inherently more stable, and we talked about that before. The wing is on top of the 172, so all of the weight is at the bottom and below the center of pressure. It makes it more stable, and it has less dihedral. You can see that there's a little bit of dihedral, and by dihedral, I mean that small angle between the horizon and where the wing comes up from the root to the tip. On low wing airplanes, you got a lot more dihedral. Look at that. See that angle? So these airplanes are just more stable because of their design and require less dihedral. Engineers have put every single angle of that airplane together very exactly. And the 172 has not changed in basic size and shape in forever, in many, many, many decades. It's a very reliable trainer. All right, I promised something about swept wings, and here we go. Swept wings airplanes will have a similar side slip characteristics, and that is as it side slips, more of that wing becomes exposed to the relative wind, which will cause a lower wing become perpendicular to the airflow, increasing the lift, and will cause that airplane to straighten up. Now, Jepsen kind of gives me a snapshot, a real quick picture of swept wings and how I can appreciate it. There's so much more going on with these airplanes. Plus, they have something called a yaw damper, which helps us to avoid any type of uncoordinated control. With a yaw damper, if I apply aileron control, the airplane automatically applies the appropriate amount of rudder. If I have a side gust from some sort of turbulent condition, the airplane will automatically adjust the rudder. In fact, on Air France 447, there's quite a few very, very smart people that agree that the yaw damper was the only thing that prevented them from entering a spin and actually spinning there. It didn't matter. I mean, everybody died anyways. I know it's horrible, but they didn't spin the airplane because of the yaw damper. So the electronics on the airplane were actually trying to work and were effective in helping that airplane somewhat. Okay? All right, keel effect. The airplane does have some rigidity in space because as I'm moving forward, if the fuselage is exposed to the relative wind, that'll cause a force. And every force has an equal and opposite force in reaction, so that will also cause the airplane to straighten up. Again, all ideas that the airplanes are inherently stable and easy to fly. Okay, here's your CG, same type of thing with side slip in an airplane. Side slip in an airplane with that keel effect. If I expose this side of the fuselage to the relative wind, that's fine. It will straighten the airplane. Now, what if I want to purposefully have the side of the airplane exposed to the relative wind? I might want that. How else would I land on that upwind tire when I'm doing my landing? I have to have, when I come in contact with the ground, a little bit of side slip. So I can purposefully do this and resist the inherent stability of the airplane by applying sufficient rudder pressure. I could do what's called a forward slip to land without flaps and still increase my descent path without increasing the speed of the airplane. I can do that easy, but I have to purposefully do it. The airplane is not designed to do that. And that's another one of the maneuvers that you'll do during your private pilot certification. All right, demonstrated stalls. Couple of stalls you guys will do. You're going to do power on stalls, you do power off stalls. So a stall where you fly the airplane as if you're taking off and leaving, or a stall as if you're approaching and landing to an airport. Some of the stalls that you'll do are only demonstrated by the instructors. And some of them come from previous accidents from decades ago and began the stall spin awareness idea or the concept. So here I've got a pilot that begins to overshoot the runway. That's fine. This pilot does not understand how to fly airplanes, especially if something unexpected occurs. They've flown with their instructor. The instructor was able to guide them through and teach them procedures. But something has unexpectedly occurred here, and that is the airplane overshot the runway. Okay. So the pilot displaces the control wheel to the right and attempt to return to the extended center line. They're trying to come back. You can see the controls, aileron and rudder. Pilot adds excessive right rudder and to increase the turn rate. So not flying coordinated and disregards that coordinated flight idea, thinks, let me just apply a lot more right rudder pressure because that's causing what I consider a good effect. Might not be though. The upper wing begins to travel faster because that circle idea still exists. That upper wing is going to travel faster, produces more lift on that wing and causes an increased bank angle. Well, if you get an increased bank angle, what do you do with the ailerons then? All right, moves the control wheel towards the left. This pilot is close to the ground and they have a right rudder pressure and a left aileron input. Does that sound correct? It doesn't. And unless I'm trying to do a slip, which a slip is how I make a crosswind landing, so that is important. But way out here on final, unless I'm trying to do a slip, this is not a good condition. Okay? So the airplane is now cross-controlled. The nose begins to drop. What do I get with increased lift everywhere? Increased drag. So increased drag, what do I get? Nose dropping. Okay, that's fine. The pilot applies back pressure to decrease the descent rate. Okay? The slow right wing drops further, increasing the angle of attack until it stalls. This is 100% a way to stall an airplane without meaning to. It's an unintentional stall. Those are the stalls that end up hurting people. Okay? So you got a cross-controlled condition. The pilot exceeded the critical angle of attack. Easy. So far, they've made a series of poor control inputs, or poor decisions even. How does that pilot get away from this? Well, they stalled the airplane, they exceeded the critical angle of attack. What do they need to do? Decrease the angle of attack. All right? We're kind of close to the ground, so what does this sound like for me? What do I need to do? Do I just decrease my pitch?
No, I think...
Pry some power as well. Yeah, full throttle, get the airplane flying, neutralize the controls. If I have rudder and aileron, just make them neutral. Okay? And the airplane will fly again. All right, let's talk a little bit here. There's coefficient of lift, that's fine. you got a stall coefficient of drag on that upgoing wing. The upgoing wing is going to stall very, very soon. Okay? And the downgoing wing will not stall as much, but both are stalled. Both wings are stalled. So if I don't apply the corrective technique, which is decrease the pitch angle and increase the power, I could for sure have a spin. And these are examples of spins. Where's the flight path? Which direction is the flight path? Every time. It's to the ground. Okay? You have an erect spin, which this is typically what we're going to have. Okay? In a Cessna 172. Inverted spin only if you're trying and you have an aerobatic airplane. All right? And a flat spin, all right, only if you're in Top Gun or something, yaw only. They said, flat spin, remember the movie Top Gun? New one's coming out pretty soon, that's exciting. But this is a spin. You're not required in your program to intentionally spin the airplane. But the airplane could spin. Again, which one of the wings are stalled? Both wings are stalled. Okay? So what's key to me getting out of this spin? What is the key function for me to recover? I got to decrease my angle of attack. But where's my flight path? Towards the earth. So where's my relative wind? From here. You can see the challenge. Okay? All right. Where did spins come from in the first place? Well, it's aerodynamically. I can't say that spins came from a certain thing or whatever. They exist. It's just a true deal. But how did we learn as aviators about spins? Well, remember, the Wright brothers started this powered flight thing anyways, right? Well, as soon as they made one, what did someone else do? Well, they had to make another. And then next thing you know, Europe starts making them, and a couple years pass. Now we have big air shows and conventions and seminars or whatever exhibitions. And now I got this person saying they can fly higher than that person. Come on, this is just the way life works, right? Of course it is. Well, they would gather around and they would attract big crowds, just like anything exciting would. They would attract big crowds, and sure enough, it'd say, okay, well, this one's going to fly higher than that one, and bet on it, or who knows what they're doing. Eventually, someone stalled the airplane. They couldn't climb anymore. When they were trying to climb, they're making competitions, and eventually someone entered a spin. Oh my gosh, that pilot crashed. This was horrifying. Why did they do that? Nobody knows. Who is the only person at that time that knew is now dead, okay? That's the only person that knew what happened before they died. Did they mean to do that? Well, it continued to happen, right? And nobody understood. The only thing people knew is that once the airplane entered this spin and started heading towards the earth, and they call it the death spiral. Once it started into this, there was no recovery. That pilot was dead, okay? And the only people that had ever spun an airplane were dead. So, one day, pilot enters a spin, and they recover. The airplane starts flying again. Of course, everybody, the family members and all this were like, oh, this person's dead, they're crying out. And everybody's excited, what the world? They all run over to that pilot. How in the world did you do that? What happened, right? That's the question. And the pilot said something remarkable. He said, you know what? I knew it was the death spiral. I knew that I was in it. So I said, let's get it over with. And he survived. Now that is just tragic, the fact that he said, let's just get this over with. And he ended up living. Okay, but that's fine. It helped everybody learn a whole lot about aerodynamics and about what's going on with the spin. I can tell you right now, both wings are stalled in the airplane. The airplane is headed towards the earth. What is the untrained? And at that time, there was no one trained, because the only people that ever experienced were dead. What does the untrained person do? Well, I want to climb. And you're making it worse, right? You're continuing to exceed the critical angle of attack. The very first thing you need to do if this happens is, I'm headed towards the earth, so don't get there in a hurry. Power goes to idle. Then what? Neutralize the controls. If I have rudders, leave them alone. If I have ailerons, leave them alone. Remember, the airplane is spinning in one direction. So one wing, the lower wing, is moving down. It's stalled worse. Okay? If I attempt to recover, what have I done with that left aileron? I've made it worse. So during the stall, yeah, if anything, if I have any kind of upset left or right, maybe some recovery with rudder is called for, but not until I'm flying. I don't want to use ailerons. Keep them neutral. So power comes to idle, neutralize my controls, and then apply rudder in the opposite direction. I promise you the airplane will fly again. Right? Just like the pilot that was up there that learned about this in the first time, he just pushed it forward, it decreased his angle of attack, and began flying again. Now I have an airplane that I can use. That I can deal with, right? Okay. All right, fine, fantastic. Let's take a look. This is just kind of aerodynamics, exactly what I was talking about. More stalled, you got a chord line, less stalled, drag, lift, all this stuff. Where's the flight path towards the ground? The incipient spin, about 4 to 6 seconds in light aircraft. This is fast. In 4 to 6 seconds is approximately 2 turns. The airplane will motion completely upside down in the beginning and then spin rapidly twice. Okay, that's the incipient spin. This is probably the most violent part of it. You can call it violent, but I call it fun. All right. The fully developed spin, this is easy. Now it's just actually spinning. You can maintain this forever. You really, really can. As long as you continue to hold back on the controls, you're spinning. Life is great. Enjoy it. Just look at them, right? The airspeed, vertical speed, all that, they're stabilized. The airplane is stabilized here. And you're only losing about 500 feet per 3-second turn. Okay. Here, you're losing about 1,500, maybe even 2,000 feet. For that first little bit, you're going down rapidly. And then the recovery. Just recover. They'll recover as soon as you release the control. A quarter to a half turn at the most. Okay. If for whatever reason you get confused or you get lost or you forget what to do, guess what? The instructions to recover from a spin are printed on the side of the airplane. You can just look and read it. It'll tell you exactly what to do. Okay? All right. By the way, there's a lot of emphasis on the spin, and I know pilots sometimes get a little bit of anxiety from it. It's fun. It really is. And unless you know how to make that happen, you're not going to make that happen. I promise you that while you're training, you may get a little bit of a wing go left or right while you're doing your stalls, but it will not spin, okay? Just release the controls, make the airplane fly again, and then start a climb, all right? All right, I got, this one was the exact same thing, auto rotation and so forth. Aggravated stall results in what's termed auto rotation. Airplane follows a downward corkscrew path. Airplane rotates around a vertical axis, rising wing less stalled than a descending wing. Both wings are stalled, creating a rolling, yawing, and pitching motion. The airplane is basically being forced downward by gravity. All right? Rolling, yawing, and pitching in a spiral path.